we're supposed to graph this rational function, h of x equals x over 2x minus 4, and then it says use a calculator as a tool, but draw the final graph on paper. Now, when we have this instruction about just using the calculator as a tool and drawing the graph on paper, the final graph, what's usually going on in this case is that the graph has a hole in it. And you remember we talked about this in the previous lesson, I think it was, a recent lesson, that some rational functions, the fraction is reducible. And then when you reduce it, you might end up with a simple formula. Maybe it's a formula for a straight line, and then you would think the graph of the function is just the straight line, but turns out no, there's a hole in the straight line, and the reason is you're actually graphing the original rational function, and there is a value for x that makes the denominator equal 0, and you have to leave that point out. And then we draw a graph on paper just because you can't really see the hole in the graph whenever you do it on a calculator. But this is actually not one of these situations, and the reason is x over 2x minus 4 cannot be reduced. And so this is a complete rational function where we're going to have different branches and asymptotes and everything, but I'm still going to go ahead and draw the graph on paper because the instruction says to do that. But this is a little bit of a trick question because of this extra instruction. The first step is let's find the asymptotes. We can find any vertical asymptotes by setting the denominator equal to 0 and figuring out what values for x make that denominator equal to 0. If 2x minus 4 equals 0, and then when we add 4 to both sides, that gives us 2x equals 4, and then dividing both sides by 2, we get x equals 2. And so that's the off-limit value for x, and then that means that the entire vertical line, x equals 2, is an asymptote. So that's a vertical asymptote. Now to find the horizontal asymptote, it's a little bit tougher. The first thing is, let's just check to see if this is a proper rational function. Remember, a proper rational function is one where the degree of the numerator is smaller than the degree of the denominator. That's not the situation here because we have a first degree expression on top. This is the same as x to the first, and then we have a first degree expression on bottom. This x is also raised to the first power. Now, in a case like this, if there is a horizontal asymptote, you can find it by calculating the ratio of the leading terms. There's just one term here on top, so the leading term is x. The leading term of 2x minus 4 is 2x. And so let's take the ratio of x to 2x, just divide those, and that gives us 1/2. So the horizontal asymptote is y equals 1/2. That's a horizontal line. Now that we've got these two, let's put a graph up, and we'll start by drawing in these asymptotes. See, here's the vertical line, x equals 2, and it crosses the x-axis at the point 2, 0. And then here's the horizontal asymptote, which crosses the y-axis at the point 0, 1/2. That's the same as 0.5. Now, to figure out the general shape of the graph, we can analyze what's going to happen to h of x as x goes to positive infinity and negative infinity, and then as it approaches the asymptotes. When x goes to positive infinity, the end behavior of the function, what's going to happen when x goes to positive infinity, the leading terms are going to take over in importance. So x and 2x will be important. Negative 4 will not be important. And when x goes to positive infinity, x divided by 2x is going to equal 1/2. Basically, the numerator will be about half the size of the denominator, and they'll both be positive. And so what's going to happen to the function is x gets infinitely large, h of x will get closer and closer to 1/2, and that's why this is a horizontal asymptote. So the curve will go like this. It'll get closer and closer to this line, y equals 1/2. Now, whenever x gets closer and closer to 2 coming from above, what if x, for example, is just a little bit over 2? Well, then we'll have a number that's a little bit bigger than 4, minus 4, and that'll be a very small number on bottom, and then we'll have something a little bit greater than 2 on top. This will be a tiny fraction on bottom and 2 on top, and that will end up being a big positive number. And so what's going to happen is the graph, as you get closer and closer to 2 from above, will go up, up, up into positive territory for y. And so basically you're going to have a branch that looks like this. And I just kind of drawn that in it's kind of sloppy, but just to give you the general idea, we're going to get the pin down where this branch is on the coordinate plane exactly in a second. But it's basically going to look like that. Now, what about when we go in the other direction? What about when we go into negative x territory as x approaches negative infinity? What's going to happen to h of x then? Well, you're going to have your leading terms take over again, but then we'll have a big negative number here on top, and then we'll have a negative number on bottom, 2x, that's twice as big. It'll actually be a little bit more than that because of the negative 4. But a negative divided by a negative is positive, and so again, h of x is going to get closer and closer to positive 1/2. And so as we move out on the x, in negative territory on the x, the graph's going to get closer and closer to 1/2 like this. And whenever we go back in and get closer and closer to positive 2 from this direction, what's going to happen? Well, when x is a little bit less than 2, then the denominator is going to be really small but negative, because it'll be 2 times something that's a little less than 2 minus 4. So 2x will be smaller than 4. It'll be a very small in magnitude negative number. And then we'll have something that's a little bit less than 2 on top. And so what's going to happen is h of x, if you plug in a number, if this isn't making much sense to you, just plug in a number. Plug in 1.9 for x. And what you'll find is 2 times 1.9 is 3.8. Minus 4, you're going to end up with a pretty small negative number down here. And then when you divide that into 1.9 on top, you're going to get a negative number that's large in magnitude. And the closer you get to 2 when you're coming from below, the larger the magnitude of the negative number. And so the curve is going to go like this, down toward the negative territory for y. And that's just an idea of what it's going to look like. It won't be exactly in that position. So this is basically what the general shape of our graph. Now to pin it down exact position of the graph, let's plot a couple of points. Let's find the Y-intercept. Looks like we're going to have a Y-intercept. Let's figure out exactly where that will be. All we have to do is put 0 in for x and then calculate the matching y value. And when we do that, we end up with 0 for y. And so actually the Y-intercept is going to be the origin. So the curve is going to go right through the origin like this and then head down into negative territory. Let's get another point on this branch of the graph. We've got x equals 2 here. That's the vertical asymptote. But let's go over to x equals 4. We'll put 4 in for x and then calculate the matching y value. And that gives us 4 over 2 times 4 minus 4. And then 2 times 4 is 8. Minus 4 is 4 on bottom. And so y equals 1. So when x is 4, y is 1. That's another point. And that's actually just right in here. And so the branch on top here should go like this. And then now I'm going to plot the finished curve, both branches of it, and show you what it looks like. See, here's the top branch, and it's supposed to go through the point 4, 1. And then here's the bottom branch, which is supposed to go through the origin. And then the end behavior is as we already discussed. And so this is the final graph of the function, and this is the answer to problem 22.